Calculating work is, of course, one of the applications of integrals. And in lesson 5.5, we look at 3 different situations that involve work, one of which is pumping fluid. On page 462, problem number 18 refers to example 6 from the reading. And I'm going to save you the boredom of watching me draw the picture again, so I've provided that here along with some of the important information from example 6. Let me just say a few words about this before we get to solving the problem from page 462. We have a cylindrical tank which is 10 meters high, has a radius of 5 meters. We are pumping to a distance 4 meters above the tank. In other words, 14 meters from the bottom of the tank. The technique, as with most of our integration problems, is to take a cross-section slice, in this case a horizontal slice, calculate the work done to move that slice, to pump that slice to that location 4 meters above the cylinder, and then sum up our slices with integration. Now, from the example, we know that water weighs 9,800 newtons per meter cubed. The slice is, of course, has a circular cross-section, so the area is going to be pi r squared, which in our case is 25 pi. The thickness of our slice, since we're slicing perpendicular to the y-axis, is dy. And then the distance that we're going to pump the slice is this distance here, which is 14 minus y. We're calculating work, and of course work is force times distance, and so the integral is going to be the force function times dx. In our case, because we're going on the y-axis, it's going to actually be f of y dy. Okay, so that's all the background on example 6. Now let's focus our attention on page 462, number 18. In this particular problem, they say, suppose that instead of being full, the tank in example 6 is only half full, which means the water goes to a distance of 5 meters. Okay. How much work does it take to pump the remaining water to a level 4 meters above the top of the tank? So we're going to steal some pieces from the integral that they used in the example. The integral that we'll use is going to be very similar to the one from example 6. We still have 245,000 pi, 25 pi times 9,800. We still have 14 minus y for the distance, and we still have dy for the thickness. However, we are only going to integrate where the water is, which in this case is 0 to 5. Now, when you do these integrals, of course, hopefully by now you've found out that you can do the integration right on your calculator. I'm going to go ahead and do it by hand. First thing I'm going to do is factor out the 245,000 pi. I think I'm missing a 0 there, huh? And once you get rid of that junk, the antiderivative here is pretty easy. Antiderivative of 14 is 14y. The antiderivative of y is 1/2 y squared. We're going to evaluate this from 0 to 5. And the good news is that when we plug in 0, this is all 0. So really all I have to do is plug in the 5. Okay. Five times 14 is, let me see, something like 70. And 1/2 times 5 squared is 12.5. 25 times 1/2 is 12.5. So far so good. 245,000 pi, and this is going to be 57.5. How's that sound? And at this point, yeah, I'm going to use a calculator. And you get a fairly large number. I'm going to write it the same way they did with the answer in the example. They didn't really use scientific notation, as you can see, because the decimal point's in the wrong position, but I'm going to be consistent with what they have. So this is approximately 44.3 times 10 to the 6th joules. And so we've answered the question. One thing to notice is, even though our cylinder is half full, it took more than half the work to pump that bottom half of water up to 14 meters. And hopefully that to you will make sense, because work is dependent on distance and it has to go farther. The bottom part has to go farther than the top part. So it's not going to be just half. And a lot of people are, when they first read that problem, think it's going to be half. At this point, these pretzels are making me thirsty, so I'm going to let you go.
You know you got what you wanted when you gave me the news. You told me you were leaving, it gave me the blues. But that's okay, be on your way, 'cause I'm sick of all your scheming. I should have known better, I just couldn't see. It's almost like a spell that you put on me. I thought you'd fly right if I just wait, but I seen the light just a little too late. And now I'm never gonna love nobody again, 'cause I'm through with dreaming. Well,